Okay, I think we're just waiting on Chrisanne. And can you guys hear me?
Yeah.
Let's try this again.
This one's the best one.
Oh, there's Chrisanne. There she is.
Yeah, I got really bored on Saturday, so instead of doing like the essay I was doing, I'm like, yo, I'm gonna get a bunch of Zoom backgrounds. It sounds fun. I downloaded like 15.
I bet it's getting boring. For some reason, it's not letting me. Oh, I bet it is crashing. Something's going on with Zoom.
Because they're using it for high school too, so.
Yeah, they're in the whole United States is using it. Probably the
That's
whole world's using
a lot of servers going up at once.
it. Yeah.
I think it's dumb that they have dedicated servers if so many people are using it. Just let it like work off of everybody else's network.
It would probably have crashed by then.
That's true, but if they have like dedicated servers, I don't think they're probably designed to handle the magnitude
No.
of people using it.
I'm sure you're right. It was never designed to
Be this much.
be for this. Okay, let's see. Can you guys see the screen now?
No. Oh yeah, there you go.
Oh, there we go.
Okay, good,
We're-
good, good. Yeah.
Micrometers.
I sent out an email last night saying I wanted you guys to look over these. One's a video and one is from Whisk online. Did you guys get this message?
Yes.
Mhm.
Okay, did you guys look at it? So before I go into the engines chapter, which is what we were going to do, I wanted to go over some review stuff with you, but I also wanted you guys to be aware that I posted this, and I will be posting before our class, obviously, but I'll be sending you guys videos and stuff that I think will help, which I use in the classroom to teach how to use these tools. Because, for example, using a bore gauge is kind of complicated. There's a bunch of steps you have to do to set the tool up for measuring the cylinder. Did anybody happen to look at how to measure the bore of the cylinder?
I remember doing it in Schulte's math class.
Okay, good. But he probably might have talked about using a telescopic gauge, or did you guys
Mhm.
talk about using a bore gauge?
There's a telescopic gauge, I'm pretty sure.
Yeah, so the telescopic gauge looks like a T. You know, it looks like this, and it expands on the bottom, and then you would stick it in a cylinder, tighten it up on the top, and pull it out, and then take a micrometer and measure that. However, because the cylinders we're working with, you cannot tell where the perfect perpendicular line is with the telescopic gauge. We use a bore gauge, and it helps us to we can calibrate it so that when we stick the tool down into the bore, we can actually tell where center is, and then if we rock either left or right, it'll tell us that we're off, so that because we can't tell whether or not the telescopic gauge is actually straight up and down in the bore. It's really, really hard to do. And I have seen machinists do it, but they've been doing it for so long, I'm pretty sure they eyeball where the center line is. But however, we're going to be using a bore gauge when we go back into the shop. And so I thought I'd send you first is how to use a micrometer, which if you took my automatic transmissions class, we went over this, but I'm going to go over it again one more time. And this method I like to use, and I just happened to find this is probably like 5 years ago, I happened to find this college that put an online video out on how to use a micrometer, and it uses counting dollars, quarters, and pennies instead of looking at the micrometer in the by thousandths, which can sometimes get confusing. And then in order to use a bore gauge, you got to use a micrometer. So we're going to go over this after we go over our review with the class. So why don't I let me So Jeff, you're in the top left-hand corner of my screen. Why don't you have? What did you cover in the material this past week that you'd like to talk about
In chapter 20.
in chapter 20, or even you guys anything you've seen online? Because I know there's a lot of online material going around right now that that you want to share about engines.
Um, can we kind of have a refresher of what we talked about last week?
Last week Tuesday we talked about VTEC, and then Thursday I did or was it cooling?
I don't know. I think we were going over block stuff.
We didn't
It
go
was-
over the. We didn't. I wrote it down. Hold on.
We started getting into it. We were like talking about like pistons and stuff like that.
We went over like the coolant system mostly on
On
Yeah.
Tuesday, I think we covered some of the on VTEC stuff. So hold on.
Yeah, today you were going to start going through the slides for the block chapter.
For chapter 20, I think I pulled. I shared L1 training, that site with you guys, and we talked about balance shafts. I think.
Yeah.
And I think somebody, was it Jet or maybe Archer? Somebody had a question about hyperprotective pistons and the coating. And then Kevin actually shared the material from chapter 20. It talks about, actually, I think Archer talked about that heat area, the heat gap that's in the piston, and that's to help prevent it from expanding. Because we don't want the pistons expanding in the cylinder. What would happen if our pistons, okay, so when we look at the piston, which we'll look at a picture of it today again, but when it's in the cylinder, what would happen if it expanded too much in the cylinder?
It gets stuck.
It would get stuck, right? And so there's some cuts
Wouldn't
that
it
are
shave
designed.
more metal?
I'm sorry, what'd you say, JT?
Wouldn't it like shave a lot of more metal than it's supposed to? Or like
It would
create a
start
lot
to.
of wear?
You're right. It would start to wear down the cylinder more and more. But at some point, when it expanded too much, it would actually just get stuck in the cylinder, right? It would cause so much heat and resistance, it would probably weld itself to the cylinder. Is actually what would happen because the motion, it would friction weld itself. If you haven't seen what friction welding is, after the class, you guys can YouTube it. They basically take two parts, put it in a lathe, and put them together in contact while they're in motion, and they friction weld itself to each other. And that's what would happen to the piston and the cylinder after it scraped up and destroyed the cylinder and the piston. So we don't want that happening, because then our engines wouldn't last, how half as long as it's designed to. If anything, it probably wouldn't even drive out of the shop. So there are, that was, I think, a question that Archer had. But I think I went over, what else did I cover last week? You guys help me out. What else did we talk about?
I took a screenshot of the hoses, like hoses failure.
Oh, that's right. It was the Gates class. I went over the Gates material from the class I took the day before, and it was talking about how coolant affects the engine if you mix the coolants together. You guys remember that?
Oh,
Yeah.
yeah.
Yeah, how we're not supposed to mix coolant because we never knew what was in there to begin with, and mixing the coolant causes chemical reactions, which makes all the components fail much quicker.
Makes Carver.
Okay. Does that help, Jeff?
Yeah.
Is there anything you wanted to talk about from last class?
The type of hose failures.
Type of hose failure. Okay, what was the most common hose failure that happened?
Isn't it ballooning or
Yeah, we have ballooning, we have cracking, but remember, we can have internal hose failures and we can have external hose failures. Jeff, what's the most common external hose failure? What happens to the hose which makes it fail?
It gets soft and spongy.
It gets soft and spongy. Okay, but what causes that soft and sponginess on the outside of the hose, not on the inside of the hose?
Heat.
Heat. Okay, but what else?
Unwanted
Remember,
chemicals.
I'm sorry. What was that, Roy?
Unwanted
Unwanted what?
chemicals.
Chemicals, right? Remember I shared with you guys that petroleum breaks down the type of material that the hoses are made out of. So people who spray their engines down to clean it up, oftentimes those chemicals they spray on are made with petroleum, and the petroleum starts to break down the chemicals that make up the hoses. So if that were to happen on the inside of the engine, for example, if we had a transcooler leak and it got into our radiator and it's got start circulating through our cooling system, we would have to change the hoses because it has petroleum in it, and it would start to break down the hoses from the inside out. So you're right, you guys. Heat does break down the hoses, and it could happen from the inside out, or the outside in with heat. But it makes the hoses crunchy at a certain point, right? The hoses actually become softer and start to break down when they're exposed to petroleum chemicals. Okay, good. Dylan, what do you want to review?
The measuring the camshaft.
Measuring the camshaft, okay.
Micrometer.
With a micrometer. Okay,
Yeah.
so we would be measuring the main caps or the main journals of the camshaft. We could also look at the profile of the. We can also look at the profile with a micrometer and look to see how many degrees it has of wear. But what did you want to talk about?
Like, so can you machine that yourself? Like, say you find that it's more worn on one side of the journal than the other. Like,
Okay.
say,
Do you have a lathe?
no.
Then you probably won't be able to machine it yourself.
Yeah, get some sandpaper. You'll be fine.
Would it be better to buy a new?
Would it be better to get new? Yes, it is always better to get new if you can afford it and that part is available. So, for example, some engines are very common and their parts are easily available, like the Toyota 22R motor. It's it's used in so many vehicles and people love those engines. So there are going to be companies who are going to reproduce those parts, even though Toyota doesn't make them anymore. There are companies like LC Engineering that makes them. So there are companies that with large machines that are able to process those kinds of parts. Does that make sense?
Yeah.
Okay. If you had a large enough lathe, I'm sure you could clean up or fix a camshaft journal if you had practice. It's not something you can just throw a camshaft in there and just grind it down. You guys understand, right? Who took brakes last year? Did you get in brakes class right now? Did you guys get the chance to use a lathe yet?
We read about them.
You read about them. Okay, so JT, you guys used lathes the brake cutting lathes last year, right?
Yeah.
Is it easy to do it? If you didn't have instructions or somebody there to guide you, could you just throw the rotor or drum in there and just say, I'm just gonna cut the thing down, right? Just to
Fuck no.
right, and the measurements on those
Because you
dials
take off so much too. That's why.
yes.
Like
The
cutting
measurements.
and resurfacing it. It's might not think that it's a lot. Like that's one thing that I remember Hussey saying is that you might not think it's a lot, but it's a lot that you're fucking taking off.
Yes, because we measure in thousandths of an inch. If you start seeing chips
Yeah.
flying off that thing, it's probably more than a thousandth of an
But
inch.
plus, looking at the dial too, having it being so worn out, and like try to like line things up.
Yes, that's what I was explaining.
It's
Was the
fucking hard.
measurement part of the lathe is it's complicated. So it's not like anybody could just go jump on a lathe and cut down metal. Like if you've ever used a wood shop lathe, it's a lot different than a metal lathe because we're using
Wood shop lathe is a lot easier.
right. It is, and wood is a lot more forgiving. So often when I used to
Yeah.
teach intro, I used to teach that you know, when you're working with wood, we can have flaws up to 1/4 of an inch, and it's acceptable in most cases because we can you know we can work around wood a little bit easier. But when you start shaving metal, we're
You
working
can't
with
put back
thousands of an
metal.
inch, and that is smaller than a human hair. So um, you know, once we cut that metal away, we can't put it back, and that's something we're going to cover when we talk about the micrometer section from WISC. Is that we cannot count metal that's not there. So um, it's a lot more complicated than it looks to. However, with some practice and some instructions, you could. I don't see why you couldn't grind down your own camshaft or crankshaft journal if you had to do it that way. Then you would just get an oversized bearing for that particular journal. You still there?
Yeah.
No. Okay. Okay. JT, you're next. Oh, did that answer your question, Dylan?
Yeah.
Okay, JT, you're next.
I don't know. I don't have anything.
You don't have anything? Did you cover any of the material this week?
Not since last week, no.
Okay. So, why don't you think of something, JT? And then I have a question from Archer. So Archer couldn't be here with us today, but he sent me an email question. And his question is there superiority in a VTEC system with engaging or disengaging large cams or versus a car with upgraded cams or permanently engaged large cams? So because this is being recorded, I wanted to answer his question with the class so that if you guys thought of something, we can share it with Archer as well. So to really answer the question, is the VTEC system superior to a stationary camshaft?
No.
Wait, is this
Well,
recording?
it depends on what you mean by superior.
Oh, is it better? And yeah, you're right, Kevin. You're absolutely right. Is it better? And the question could go either way, right? Can it fail easier than a regular camshaft? Probably, right? There's a lot more moving parts. If you don't change your oil, if you don't have enough oil, if you have the wrong oil, it could definitely affect VTEC, right? As Jason knows, if you don't have enough oil, VTEC's probably not going to work, right?
Yeah, I have a question about that later, but
Well, you're coming up next, so you can.
okay.
Well, yeah, you can ask your question, but in a lot of ways, VTEC is superior because it gives you the best of both worlds, right? We get fuel economy, and that's what it was designed for. I believe VTEC was designed at a time when fuel prices had started to rise. Have you guys been keeping up with fuel? Yesterday, I watched a video on CNN. I don't know if it's totally true or not, but OPEC has shut down a lot of oil production because nobody's traveling and nobody, planes aren't flying. So,
Well, they tried.
yeah,
They tried a while back, but so now the May oil futures sellers are paying $37 so that buyers will take it.
yeah, they can't get rid of it. They can't even give it away. There's so much oil right now. they can't give the fuel away. So,
but that's just that's under what they call the futures contracts. I mean, but you're right. So basically, nobody wants oil right now because there's just too much of it.
yes,
And so for the first time ever, the futures contracts have gone negative, where sellers have to pay buyers to take the oil. Theoretically.
Yes. My link to this was that VTEC came in a time. Let's back up a second. Where is VTEC found? What cars?
Hondas.
Rice cars.
Hondas. Where is Honda from?
Japan.
Japan.
Japan. Does Japan have its own oil sources?
Nope.
No, they buy and import all their oil, just like Hawaii, right? We have to bring in our own oil. Although Japan's a island country, and so they have to find a country that will sell them oil. So can you guys imagine if there are any embargoes or there's something going on, a war or something like that, and nobody will sell their oil to Japan? What happens to the price of fuel in Japan?
What's that?
Skyrockets.
It skyrockets, right? And so VTEC came about in a time where fuel prices were probably high, but people still wanted to go fast, right? So they said, well, we can give you fuel economy and you can still go fast, because most of the vehicles in Japan are, you know, are very small.
Four
So
bangers.
right, or
Compact.
even
Oh, they're like 3 bangers.
2-cylinder, 3-cylinder
Mhm.
cars, and what most of their vehicles are designed to only carry 1 or 2 people. It's not like they drive around SUVs to go to the store, right? It would just be a total waste of money to them because their fuel prices are so high. So VTEC was designed to give you fuel economy as well as power. So the discussion we can have is it better? And the only way I could see that it's better is that it still gives you fuel economy. However, if you wanted power all the time to go as fast as possible, I don't think VTEC is the way to go, only because it's got so many moving components. So I hope that answers Archer's question. Can you guys think of anything else that I might have missed?
Well, I think the other thing it does at low RPMs, it makes a smoother engine. And so that you have, it gives you the torque and power at high RPM, but you also have the smoother, more fuel efficient engine at low RPM. Because if you have a radical cam permanently in your car, when you're idling, it's just gonna almost
You're losing vacuum.
and it's almost gonna sound like it's gonna die out if you don't get some RPMs up to it.
Right, you're right. So it is a smoother engine. You're correct. So it's kind of finding the balance between both high performance or mid-range performance, because most VTECs don't come stock at the high performance design, and also getting fuel economy and good vacuum and a smooth running engine. So that's right. Okay. Jason, your turn.
Okay, so going back to VTEC stuff. So I tuned my car and I set my VTEC to hit at 5. And when I was testing it out,
Exploded.
I would hit 5 and my VTEC wouldn't kick on, and then it would kick on all the way to like 7,000 RPM. So I don't know
It might need to be reprogrammed. You might have to get Hondata.
No, I do have Hondata.
Okay. And you
But I don't
reprogrammed
know
it to 5?
Yeah, and I checked my map, and I checked my map, and it said that it's at 5, and I have an app because I have the V3.
Okay,
and
Jason, did you check your oil pressure?
I don't know. I can't check my. I don't have a.
You might want to make sure that you're supplying enough oil to the
Yeah,
VTEC solenoid.
Yeah, I don't know if it's because my solenoid's bad, or if I would it be because I have a bad oil pump and it's not pumping enough oil pressure into
It is possible, or you might not have enough. You might be losing oil pressure somewhere in the engine, and maybe that's why you're smoking so much. So I would start off with the basics before you demand more power from your engine.
Yeah, because I bought a new solenoid because my solenoid was giving me problems anyway. So.
Did you do compression tests on your engine?
Yeah.
Was it good?
I mean, it's lower compression because I have the 3 head gaskets.
Oh, that's right. I don't know. I would make a list, Jason, of what you know and what you don't know, and then test the unknowns, so that you can answer your unknown questions.
Yeah.
before you
Could it-
start throwing money at it, like at a VTEC solenoid or
Yeah.
and then you find out that you didn't have enough oil pressure to kick VTEC in at that higher RPM range.
Could it be my oil pressure switch or sensor?
Could be. It could be. So that's why you have to put a list of what you know and what you don't know, and then answer
Yeah.
the unknowns before you start demanding more power from your engine.
Yeah.
That's only fair to your engine, right? I mean,
Yeah.
you can't expect VTEC to kick in if your oil pressure is saying that
Yeah.
it's lower than it's supposed to be.
Yeah. Yeah. I mean, my engine gives plenty of power, but I just trying to get my VTEC to work right now.
Okay. Well, like I said, make a list and then try to answer those unknown questions in the list first before so that you can answer your own questions.
Yeah.
Because you can ask me, like, could it be the oil pressure sensor? And I could say yes, but I don't know what your oil pressure sensor is reading at or how much your oil pressure is. So
Yeah.
that's something you'd have to test for.
So how would you test the switch?
Well, the switch is either on or off, so it's going to be set at a certain pressure, either
Yeah.
open or closed, right? So if it's designed to open at a certain or close at a certain pressure, you would have to check to see if it's open or closed at that pressure.
Okay.
Just like any other switch, if it's coolant or oil,
Yeah.
pressure controlled. Yeah. Okay. Does that help?
Yeah.
Okay. Let's see. Jeff, you went already. JT, you got to come up with something.
Yep.
I don't got anything.
You don't have anything. Okay. Roy, did you go yet? No. Okay, your turn.
Lawrence,
Yes.
I got a question on the drive belt because I'm gonna be doing a work on my mom's car, and I heard during class that you have to get a laser or something to make sure the drive belts are aligned.
Okay. The laser helps because sometimes the pulleys are not lined up with each other. However, you could use a string with some sort of weight, kind of like a plumb bob kind of deal, and you
Yeah.
can go try to arrange it from pulley to pulley and look to see if any of the pulleys are not aligned. The only reason we would use a laser is to see if the pulleys were aligned so that it wouldn't wear out the new belt or cause any sound issues.
Okay.
Okay.
All right. Good.
Devin?
I kind of have like a question, a little bit about the material, but like I could figure it out. But I kind of have like a diagnostics question.
Sure. Shoot.
My mom has a Mini Cooper S, and sometimes when you start it up, it just like kind of like fizzles out, and then you have to
that the one
start
with
it
the
again. It goes fine.
supercharger?
Yeah.
Okay.
Could that be like a problem with the supercharger or something like that? Maybe something with the belt.
It could be a fuel pressure problem too.
Yeah, that's what I was thinking.
It could be a dirty filter, or maybe the pump's
Mhm.
starting to go out. But
Yeah, there's a bunch of like seals in the fueling system that are like bad, and you can like really smell it. We don't really care because we like the smell of the nice 93 octane fuel, but that could be causing that problem.
Yeah, it's probably on the charcoal canister side or the emission side of the engine, but it's also possible that you're getting a vapor lock issue in the beginning when you're cranking the engine. So maybe check your gas cap. The way I don't know how you guys would do something like this at home because you don't have a smoking machine, but you would need some kind of vapor smoking machine to smoke the emission system or the whole fuel system to see if it's leaking out of the cap, or if the cap is not if the cap is holding pressure and not releasing it. Oh,
Mhm.
actually, the cap wouldn't do that at this point. The emission system would. So it's possible that maybe your charcoal canister got damaged or something like that. I don't know. If you smell
Mhm.
fuel, it's got to leak somewhere.
Mhm. Yeah. It's got like 120,000 miles, so it's definitely not surprising that there's issues. But
Yeah, it might not be. It might not even be worth fixing that problem.
yeah, it doesn't. Yeah, it doesn't really bother anyone. I was just a little confused on it because it's pretty weird.
Yeah, I've worked on a lot of Mini Coopers, and I mean, have you changed the fuel pump yet?
Mm-mm.
Yeah, it's possible that the fuel pump is the
Mhm.
cause of your delay start. If you're
Yeah.
coming back for fuels and ignitions, if we do have class, you bring it in and we can throw a scope on it and we can actually see the commutator in the pump
Nice.
starting to go bad. If your car's still running by then.
Mhm. Hopefully.
Yeah. Okay. Kevin, your turn.
Well, the thing about the heuretic pistons, it seems like all they are is just they're just made with a aluminum alloy that has silicone in it, and so I'm just wondering what's different between them and other aluminum alloy pistons.
I think it's how much silicone is inside the hyperrotectic pistons, right?
Yeah. I just didn't know why it was so special.
I think it's just how much silicone is inside of the piston. You know, I thought it had something to do with how thin that part of the skirt was.
Well, they were saying the entire piston is made out of it, and it's just an aluminum alloy. Of course, everything, even steel, is an alloy. So I just didn't know why having 16 to 19% silicone in the alloy made it so special.
It had something to do with preventing it from expanding. But you know what? I'll clarify your question. Give me some time. I'll go look it up.
Okay. I mean, they did say that having that piston allowed smaller cylinder wall clearances, and that it was actually a very strong alloy. So it was less expensive, but almost as good as a forged piston.
Probably has to do with the price of it.
Well, that's what they said mostly it was price. It was less expensive than a forged piston, but stronger than a cast piston.
It's probably easier to make than a forged piston.
Okay. It's just what they gave it a weird name, and I'm just wondering why it was so special.
Why it was so special. I'll try to find out more information for the next class for Thursday. Okay. I honestly I don't know, and I know I'm the teacher, but for some of this stuff, I almost don't even really care about it. I know it sounds bad, but I want to find. I will find out the answer for you. However,
I can look it up too, so
yeah,
I can start checking it out. It was just something that sounded strange. They made such a big deal about it in the CDX, and so
you know what
it seems like just another alloy, just another metal alloy.
There's another. I have an engine's book here from like the 80s, and I'll go look in there. But I think it has to do with the fact that it just made the process of producing that piston cheaper.
Okay.
And it was just a different process than forging or casting it. So it just made more options with the manufacturer for cost of piston production.
Okay.
Okay. All right, Chris Ann, your turn.
For Lectude, since we don't have the engines stuff yet, are we being graded for that?
No.
No.
You're not
Okay.
being graded. I just wanted to give you another option for learning the material. Like there were some of the students were asking because we were going through the class, right? Like I sent an email last night and explained that I'm not going to be grading you guys from it, and so I assigned quizzes, which you could assume would be graded, and I'm not going to grade anything you do from Electude, but it just gives you another chance to learn. That's all. Okay, so I am expecting you to do the CDX work because that's where the grade book is in. Just like I think I've explained this in AC class. If you guys had AC with me, I assigned AC theory from Electude, but I wasn't going to grade you from it because all of our grade book is in CDX. I feel like that makes it more fair because you guys can track your own grade throughout the course on CDX, but Electude doesn't have as good of a grade book.
Okay.
Okay, does that make sense?
Yeah.
Okay, Dylan, did you go? Oh, you went already. Everybody go except JT. JT, nothing. Did you think of something? Okay. All right. So that's before we move into chapter 20. I thought it was important for you guys to share. Let's go over the micrometer. So I know that you guys, some of you will remember this and you might think it's elementary. However, I think it's good practice to keep up with how to use a tool, especially if you don't have that much practice with the tool. Hey, can I ask you guys a question? Of this class, how many of you took powertrain? Okay, so we got Jason. Okay, so only 3 of you? Okay, did you guys take Autotrans? You did, right? I don't understand. For some reason they have Autotrans in fall, but it's always been taught powertrain first. Anyway, I just thought of that as a quick question.
On my schedule, they're both in the spring.
I don't understand what's going on.
Yeah, I don't either. It's a little messed up.
Yeah, it's really messed up. And I've been talking to I talked to our dean yesterday, and so she scheduled a meeting for tomorrow morning to try to discuss this. But I don't understand what's happening. I just thought I'd ask real quick how many of you actually took the class, because I feel like powertrain should be in fall so that you guys can learn the basics of gear ratios and how to pull a CV axle, that kind of stuff. But I'll talk to you guys about it later.
It's weird. I have Diag as well, and I'm like, I can't take Diag until I take these classes. So
yes.
How is that being put there?
Yeah,
I keep moving my schedule for 3 years, and she keeps changing it back, and I'm like, I can't graduate in 2 years.
Yeah, just to be honest with all of you, I think our program's going to shift into 3 years because of the situation that's going on.
Just for now, just because of how it is.
Yeah, it's
like all the people who are starting fresh now, they're still going to be on the 2-year track. But if you started with the old schedule your first semester and then they change it to the new one now, it's going to be 3 years.
Depends on how many
really
you are, though.
sucks.
Yeah, it depends when you. So the people who are coming in fall, will definitely have a different. We'll be in track to graduate on time. But you guys who are in the old map, I might be a little delayed, and I think that's where they're trying to sort that out at the moment. So hang on. Here's the micrometer. Can you guys see this? Okay, so this is the easiest way, the easiest method to learn how and to remember how to use a micrometer. Because if you never touch a micrometer again after this class, which you not necessarily would happen, because you would use it in brakes and you would use it in Autotrans and in powertrain. So, but if you left our program, this would hopefully stick with you guys for the rest of your life because it's so easy to understand.
Welcome to reading an inch micrometer.
Can you guys hear this?
Yes, sir.
Okay. Share the computer something. Let me make sure. All right.
But the video is pretty sketchy. It's pretty
Ooh, that's a nice echo.
Every occupation in the machine tool industry requires the use of precision measuring tools. In this unit, you'll learn the basics of micrometer measurement. A micrometer can use metric measurements. However, this learning activity will focus on an inch micrometer. A micrometer is a precision measuring instrument that has many applications. Micrometer readings are in decimal form. Check your knowledge of decimals now by dragging the values to the correct spaces on the bottom of your screen.
Okay, let's drag these out so you guys all have a good. So I know that you guys have a good understanding of where the places go. So where does tens go? Why don't we start this off like this? So Jason, I'll go down the list just like I did with the review. Jason, where do the tens go?
The tens?
Yep.
Two places to the yeah. Just right above it.
Right above it, right here.
Yeah.
Okay. Okay. Where do thousands go? JT. JT. Okay, I'll skip him.
Yep.
Roy. Oh, JT. Where do thousands go?
Space to the right.
To the right of the decimal.
Two spaces
Right here.
to the right.
Yeah, T said 2 spaces to the right of the decimal point.
Okay, sorry, I couldn't hear. 1, 2. You sure, right here?
Yep.
It won't let me drop it there, so it's got to be wrong.
The next one over.
I'm sorry, say that again.
All the way to the right.
All the way to the right? Okay, good. Okay, Roy, where do ones go?
Right by the tens. On
To
the
the right
right
of
hand
the
side. Yeah.
Okay, Devin, where do the hundreds go?
Those go right next to the thousands.
Okay, Kevin, where do the thousands go?
Did you say me or Devin?
No, Kevin. Yeah, you're next.
Okay, goes to the very left of the scale.
Okay, good. Okay, Chrisanne, where do the tens go?
One piece to right after the decimal.
Okay, good. And then Dylan, you're lucky. You lucked out. Hundreds only go in one place. Okay, you guys see the breakdown of the words. So don't try to emphasize when you're talking about hundreds or hundredths. There's a difference between the two, and the number can be drastic, especially when we're talking about metal, right? If we're going to say tell the machinist like, I need this much, taken off of the block. The best way to do it is actually write it down. And if you have a good machinist, he'll actually go remeasure what you're claiming to make sure that he doesn't remove too much material. So a really good example of this is if you were trying to get your engine block machined, and you're going to say, I'm ordering 30 thousandths over pistons, the machinist would actually wait till you gave him the pistons, because he's going to measure the pistons and cut them according to the size of the pistons. Because if he cuts it too big, you can't put that material back, and your pistons will no longer work. So it creates a larger problem, and so he'll actually check before cutting the block or boring the block. So just remember that for the future. If you are doing any work at home and you're like, oh, I'm just going to take it to Sakey's and tell him I need this much taken out, without the new pistons you want put in the engine, they will not bore the block without the new pistons. There used to be a machinist in Happy Valley. His name was Stan, and Stan did all the machining for the students up to 2 years ago, and he's actually retired now. He actually said he was retiring for 10 years, but his wife passed away, and he basically just stopped machining it altogether. He's the you've done any work, engine work to Toyotas, and you needed any machining, he was the guy to see for a long time, probably 20 or almost 30 years. But just remember that for the future, that you cannot have any machine work done without the component that you were replacing in that engine. Okay, let's move forward. Now that you
Reading a
guys are in
micrometer
a good
can be
place.
compared to counting money.
Okay, so if we look down here at this scale, this is considered, these whole numbers from 0 to 1, 1 to 2, 2 to 3, those are considered dollars. And if you think about it, in between those dollar or those whole marks are considered quarters. So we have quarters, 4 quarters make up a dollar. And on the very end here, on the thimble, we have pennies. And so you guys will see how this lines up in a minute. Just remember quarters, dollars, pennies. So we're going to count that in that order, as if you were counting change.
When you add all of the coins and cash together, you have a total of $3.88. If you remove the dollar sign and move the decimal point one place to the left, your measurement is 388 thousandths of an inch.
Okay, you guys see the theory going on here? I know we're gonna repeat this several times, because if I just stopped here, it most likely won't get burned into your memory the same way as if we repeat this over and over. And there's some other parts of this theory that has to be covered too as well. For example, can you see the 4 here? So we have 1, 2, 3, 4. Where can you see that the fourth dollar?
No.
Well, you can see the dollar or the fourth number here, but you can't actually see that line, and so we cannot count that next dollar up. However, if you were on 0 on the thimble side here, you could count it if it was up to the 4 line. And really where this is going to come down to is you calibrating the tool first. So on Electude, the assignments that I gave you, there actually is a chapter just for engine tooling, and I think it would be important for you guys to go through this. It covers the vernier caliper, the micrometer, bore gauge, and some other tools. And I think with that material alone in that chapter, you guys should come up with some interesting questions. However, this is the best way I found. I have my own micrometer set, and our school has some, but this is the best method I found for using a micrometer. Along with those lines, there are some micrometers that break down even further, but we don't need to know that number as far down in the measurement as a machinist does. So some machining parts are so precise, they go into to pass what we're looking at here, the 100,000 mark. Okay. Yeah, but it's really rare that would that you would have to machine something down into like a half of 100,000 or something like that. So I don't know if you guys ever seen like on Instagram or Facebook where there's some machinists out there that have machined parts. When they put them together, it like sinks into each other and it looks like it's one whole piece. Have you seen that before? Yeah, there's some videos they have where people put these puzzle things together and they like slide into each other, and the pieces are so machined well that you can't even see the seam. And that's where I think that it would come down into polishing apart that fine. Anyway, let's continue with this.
Well, I wanted to ask real quick what we're supposed to do if it is in between.
You count the number before. So for example,
so you always round down, or you try to judge halfway to?
No, you always have to round down.
Always round down.
Yes,
okay.
Because that metal doesn't exist. Like that, the space you're measuring, you would go back to the smallest number. So for example, if you were in between 12 and 13 on the penny side on the thimble here, you would count the 12. Unless your micrometer had the halves of 100 thousandths, then you could actually go in between. So it'd say like 12 and a half or something like that. You can't assume that what you're looking at is 12 and a half unless there was a 12 and a half mark there.
Okay. I just want to know how they treated it. That's all.
Yeah, that's how they would do it, is just in between on the penny side, because, or even like this where you see there's 75 cents, or in 3/4 of the way to the 4, you can see that line. Then the 13 would make up the space for that, but anything in between that you would have to round down. Okay, so you guys see how this works? So we have we can count the dollars here because we can move faster. So we count $1, 2, 3, $3 we can see. We can't see the $4. We put the $3 there, and then we can count 75 cents, so 25, 50, 75. We can't count that $4 because we can't see it, and then we just count the pennies up to that point, add it all up, and move the decimal point over 1. That's the trick with reading the micrometer. I know Schulte covers it in his math class, but this is the fastest way to do it, and you can do it in your head. However, I oftentimes will recommend, like when you do auto trans or engine stuff, you write it down, and that way there are no mistakes. If you had to hand your notepad over to somebody else, like a machinist, you could say, this is what I measured here at the top of the cylinder, the middle of the cylinder, at the bottom of the cylinder, this is the cylinder taper, and it's all written out. So the video that I assigned you guys to watch, it actually talks about auto round, cylinder taper, and bore measurements, and you would write all that down. That's actually, I think, 3 task sheets that are due for measuring the cylinder. So you're going to have to use the bore gauge, use a micrometer to set up the bore gauge, and then use the bore gauge and take measurements from there. Okay, let's move forward.
Now it's your turn. To answer the following 11 questions, look at the micrometer and enter the measurement in the space provided. Give your answer to the thousandth place and include the leading 0. Select the Check Answer button to see if your answer is correct.
Okay, so can anybody tell me what this would be without the $sign or adding it up? I mean, it's a pretty easy one.
1.
Yeah, it's just 1.
No,
Wouldn't
but
it be 0.100?
Okay, so how would you say that?
1,000.
1,000. Or 100th.
That's 100,000 of an inch. Yeah. So it'd be point, or you could, I like to do it, I like to add the 0 in here so there's no mistakes where the decimal point is. So I like to always add a 0 in so that you don't make a mistake of assuming that the decimal point was in a different place. So 100, and it would be of an inch now, but you don't have to put the inch in here.
That's 1/10, right?
That's 100
of an inch.
Thousandths of an inch.
I mean, it is 1/10 of an inch. Also, it's the same thing.
Oh, okay.
It is. You're right. But
the thing is, when you say 1/10 of an inch, you're limiting your significant digits, so it's not as precise.
Right. That's the best way to answer that. And also, if we were to add like say 20 thousandths on here, how would you say that with tenths? It's no longer a tenth of an inch, is it? It's 120 thousandths of an inch. So that's where it becomes complicated if you were to tell a machinist, or if you were looking for an oversized or undersized part at a part store. Does that make sense? Okay.
Yes.
So that's 100 thousandths of an inch. If you were to actually so check this out. We'll start at 100 thousandths. If we go like this, what is this called? I think I did this in AutoTrans.
100.
10,000.
That's 10 thousandths of an inch.
Oh my God.
And if we go like this, what is that?
100,000.
That's 1,000.
1,000.
So 1,000, 10 thousandths, 100 thousandths.
Mm-hmm.
of an inch. You got to remember
My
because
my
Oh, I
brain
see.
keeps messing with me. I keep hearing like 100,000, 10,000. I'm like, okay, no, that's not what he said.
yeah. um, I'll tell you my secret. So, when we measure spark plugs, the old way was the gap used to have to be 30 thousandths of an inch. It is no longer that way. But with the older cars, like when they were carbureted, we'll say 30 years ago, the old measurements were pretty much always around 30 thousandths of an inch. That spark plug gap between the ground electrode and the positive electrode was around 30 thousandths of an inch. So if you set it to 30 thousandths of an inch, you would most likely be okay. That's how I remember it. And then the points for the ignition system was always 20 thousandths of an inch. So I always remember 10 because the tenths place so I always say 010 is 10 thousandths. And if you move it out further, the thousandths place, if you took 10 or if you took 9, so we'll move it like this. So just watch this for a second and listen. Hopefully it'll make sense. If I added 9 more thousandths to this, I would get 10 thousandths. Does that make sense? Now if I added 90 more of these, 90, not 9, 90 more, then I get 100 thousandths. Does that make sense?
Yes.
Okay, so if you remember, at the thousandths place is 0.001 thousandths. If I just add numbers onto there, it moves the decimal point over and it changes my thousandths to 10 thousandths or 100 thousandths. Okay, let's move forward. Okay, so let's add this up. How many dollars do we have?
0.
We have $0. So we break it down to a smaller scale. How many quarters do we have?
75.
Or 3 quarters.
We have 3 quarters, yeah. So I'll do it like this. So I know it's, for some of you, it's going to seem elementary. I'm not trying to, dumb this down. I just want to make sure everybody's on the same page here. So we got 0.75. So it's 75 cents because we're counting 3 quarters. And then we have 0 pennies. You guys see that? So what's the rule here? We add this up, right? So it's going to be 0.75, and then we move the decimal place over 1. So the answer here is 75 thousandths, right?
Yes.
Does that make sense? Okay. You see that? If you were writing this down, you'd always make sure you had. I would always recommend you guys put a 0 before this and an inch sign after, so that nobody could mix this up with metric or standard, and then you always knew that there was nothing before this. So for example, on the frame of your micrometer, it's going to have a number to a number. So for example, we'll say this is the 0 to 1 micrometer. The smallest number here is what you're going to count before the decimal. So if this was we'll say this is a 3 to 5 inch micrometer, this would be, after you did this measurement here, you would then go back down here and add a 3 to this because the frame size is 3. The smallest number on that frame is 3. Does that make sense?
Mm-hmm.
Does that make sense? Okay, so don't forget that whatever micrometer frame you're using, you want to put that smallest number before this. Now, if you were using the 0 to 1 micrometer, there would be no number here because it hasn't reached the 1 inch yet. Okay. How many dollars do we have, guys?
1.
How many quarters do we have after the 1?
2.
There's 3, right? 1, 2,
3.
We don't have a 4th one yet. We can see the number, but we don't have a 4th number here because we haven't reached the 0 on the thimble yet. So we can only count the lines that we see, and we know that's true because the pennies tell us so. It hasn't reached the next 0 yet. So we have 0.75, and then we have
22.
22 pennies, right?
20.
22. So we add that up, it's 1.97, right?
Mhm.
7. Then we would move the decimal place over 1,
197.
and it would become 0.97. So how would we say that?
197 thousandths.
Good. 197 thousandths of an inch. Now what do we see? How many dollars do we have?
2.
2.00.
1 quarter.
We have 1 quarter, so that's 25 cents
15 pennies.
and 15 pennies. 0.15. We add that up, we get 240,
40.
right?
200.
Mhm.
240. Move the decimal point over 1, so we have
240 thousandths of an inch.
good 240 thousandths of an inch. I will tell you guys a secret. If you were to say go to a machining school or something like that, they wouldn't teach you this. Most likely, they wouldn't teach you this method. You would just have to remember. You would have to remember this in a different way. I'm not sure how Schulte teaches this, but this is the easiest way I've learned to remember this and to teach it. And so, if you do it this way every time, you will make almost a minimal amount of mistakes, which is very important when we're talking about ordering parts or having a machinist take down metal. Okay, especially when we're doing 100 measurements. You know what I mean? Like if you have a page of each piston you're doing, or each cylinder, we're doing like 6 or so 9 measurements for each cylinder. You multiply that times 8. That is 72 measurements. To come up with your different measurements of bore and out round and taper. You guys understand what I'm saying?
Yeah.
So if you were doing repeat measurements like this, you'd wanna find the easiest method, and this is what I found. You'd be surprised how many mechanics right now don't know how to read this. And so this I made it one of my goals when I first started teaching more classes was to make some of this complicated stuff as understandable as possible. Okay, how many dollars do we have?
5.
5. How many quarters do we have?
3.
3. We can count that third one because we're at 0, right? Does that make sense?
Mm-hmm.
Okay,
Yeah.
so we have 575. Move the decimal over. We have 575,000.
575,000.
Is that fair? Okay, let's go.
Yes, sir.
Okay, good. Now we're getting faster, right? How many dollars do we have?
0.
0. How many quarters do we have? 2.
2.
We're on the line, the 0 line, so we can count that as 50. So how would we say this? 50 thousandths, right? So 0, 0. We got a couple more, I think, to do. Okay, Chrisanne, how about you? How many dollars do you see?
There's 1.
1. Yeah, 1. So do 1.00. How many quarters you see? Oops.
None.
None, yeah. But we are past the solid line, and we're past that by 8 pennies, right? So do. Oops. So we have, if we add this together, we end up with 1.08. Move the decimal over. Well, how would you say that?
108 thousandths.
Good. Yeah, 108 thousandths of an inch. I don't know. Is this a tricky one? JT, are you there?
Easy.
JT?
That's 17 cents.
Okay, somebody's trying. Okay, that's okay if your internet's not working right, but try to, if you can. You know, the school has a policy with Zoom. I just want to share this with you guys. the school actually has a policy that when you guys have to log in for Zoom classes, you're supposed to share video, because that it tells the teacher that you're there. Like I've been explaining this over the last few weeks. We've been doing this, but I understand if your internet's not working right, that's all right. But make sure you can participate when you're able to. So, like Roy said, it's 17 cents. There's no dollars, no quarters. We're at 17. So, what would we do here? Anybody can answer. Maybe you can answer, Dylan.
You move the decimal and put a 0 in
Okay,
front.
where do we put the 0?
In front of the 1.
In front of the 1?
Behind the 1, yeah.
Okay, so how would we say this, Dylan?
17 thousandths.
Good. Good, you guys. Oh, sorry, JT. I just got your message. Okay,
Wow.
how about this one, Jason?
That is so $4. That's 5, right? For the pennies. That's 5, correct?
Yes.
Okay. So that's 420, or no, 430.
Yep,
Of an inch.
430,000. So you just added 25 to the 5 to the 25. It's 30. 430,000. Good. Let's check. Okay, good. Okay. Who hasn't done? Who's still? Is Jeff still? Oh no.
Yeah.
Jeff.
I didn't leave.
Okay. I shrink my screen down so it doesn't take up
Oh.
my laptop screen, so I can't see everybody's picture at one time. So what is this one?
So we have $3.
$2?
$3.
$3. Okay, good.
25 cents and 7. Oh yeah, 25 and then 17 pennies. 3 plus 25, 17.
Okay, how does that add to?
142,000.
Yep, 42. So 342.
Yeah, 25 plus 17 is. Yeah.
42,000 is good. All right, I think everybody's got this one down. Would that be fair to say that? Would you guys remember this for the rest of your lives if you had to?
Yep. Quarters, dollars, quarters, pennies.
Just remember though, the tricks that I've seen people forget is that you have to count the frame. So for example, if this was a 1 to 2 inch frame, which you'll say at the bottom of the C. So if you're looking at the micrometer frame, which is that C part of it, at the bottom part of the micrometer frame, there's always going to have a number range between 1 and 2 or 0 and 1.
Mm-hmm.
And that's you have to add that number into the beginning of your measurement, because that's what's giving you your total inch size added into whatever you're counting on the micrometer. Okay. The next video, the next part I want to share with you guys is that video, and that is how to use a bore gauge. You guys want a break real quick? Or we have about 15 more minutes. I want to keep you on. Oh shoot, or 20 minutes.
No matter.
Awesome.
I don't really care.
Wait, true.
Okay. Make sure I'm sharing my screen. I know I assigned this to you guys. I told you guys to watch it, but I'm gonna play it anyway so we can talk about it.
96.
Liberty Mutual.
Cut.
At Liberty Mutual.
Cut.
We're going to demonstrate how to measure a cylinder of an engine. And when we measure it, we're measuring it for 3 things. For its bore, size.
Can everybody hear this?
Yeah. Yes.
I'm gonna turn the volume up. So just wave at me on the screen if you have a question, okay?
Size for its taper, so whether it's wider at the bottom or the top, and for its out of round, whether it is perfectly round or whether it's oval shaped. And we're going to do that with a dial bore gauge. Of course, a dial bore gauge can't measure anything by itself, and so we're going to use a micrometer to set this at 0. So we found the specification. Right here, the standard diameter for the cylinder bore is 3.7795 inches. It gives us a range, but we're going to set it at the lower number. So I'm going to set the micrometer at 3.7795. We've got it set already and locked. Then we'll take this to a vise. I put a rag in the vise and I set this inside of here just lightly, and then I very lightly tighten that down. Don't tighten it very much or you'll distort this. Then we find the appropriate attachments for this dial bore gauge.
Okay, good. It paused. Micrometers are very sensitive tools. Before you even start to measure anything with this, they have to be calibrated. So in the box of micrometers, there is a calibrating rod, and there's going to be a calibrating rod for each micrometer frame jump size. So for the 0 to 1, it's going to go 1 inch basically, and you're going to calibrate it by tightening up the thimble area to 1 inch, and then it's going to say 000 across the range. If it doesn't, there are these little hook tools that are inside of the box of micrometers, and you would actually turn the side down here. There's a sleeve that actually can spin, and you would actually turn it to line up the zeros with each other before you even do any measurements. So he kind of skipped through that in this video, which is okay, but you want to make sure that the last person who used the tool, especially because the school's tools are shared, right? Everybody's not as careful with them. So you want to make sure that that tool is calibrated for what you are intending it to be measuring to. Otherwise, your whole set of measurements could be off. Does that make sense to everybody? Okay, good.
We've already done that. And we put it in here in between.
Let me back it up for a second.
The micrometer. Distort this. Then we find the appropriate attachments for this dial bore gauge. We've already done that.
Okay, so the attachment he's talking about is this rod. Can you guys see my mouse traveling here? There are different length rods that you would have to screw into the actual bore gauge. So there's a tightening nut right here. This rod that goes in, there's different length rods. So they might start off at 1 inch and it might go up to like 5 inches, depending on what size you were trying to measure of your bore.
And we put it in here in between the micrometer. And then I'm going to rock this back and forth, and when we see that dial, or that needle, change directions. And this is probably the trickiest part of this whole operation, is getting this set to 0. It's close already. I'm holding the back and rocking it. You'll notice that needle's turning around. Let's see, where's it at? It's really close to 0. Let's turn just a little bit more. Okay, I think we're there. The needle's turning around right at the 0. So I'll carefully pull it out.
So what he didn't show you was when the needle started to reverse its motion, he actually moved the face of the bore gauge to 0 on that line. So you can actually turn it, turn the face so that the 0 line lined up with where it started to reverse backwards. I sent everybody this video because I want you to watch it as many times as you need to understand what he's saying. I've been using this video for the last couple of years because you can see it as many times as you need to, because we only have a couple bore gauges. So by the time you get it in a group, you guys want to take your measurements, and not everybody really understands how the tool works. So please watch this video. When we get back in the shop, we can actually use the tool. But I'm gonna back this up again so you guys can see this. What he's doing. So you'll see it start to, the needle will start to go one direction and then it bounces backwards, which means it's either the cylinder you're measuring would actually get bigger, because if the number got smaller, that means that the cylinder was actually tapered in or narrowed in that section. So watch.
I'm holding the back and rocking it. You'll notice that needle's turning around. Let's see, where's it at? It's really close to zero. Let's turn just a little bit more. Okay, I think we're there.
The face right there to make
The needle's turning around right at the zero. So I'll carefully pull it out.
the point of the needle moving.
And we'll come over here to the engine block. We'll start with cylinder number 1. And what I'm going to do is make myself a chart. So we're going to measure each cylinder in 6 different places. 3 at the top and 3 at the bottom. So I'll make a chart like this. Kind of works. Cylinder number 1, top, bottom. And then I'm going to say position 1, position 2, and position 3. Now I'm going to take my measurements. So I'm always going to use position 1 as it's perpendicular to the engine block. This is the direction that the piston would rock back and forth, and so this is...
Do you guys remember what that location of the piston would be called as it's moving up and down in the cylinder? This perpendicular spot he's talking about, what's that called on the... What is that? That type of wear pattern for that motion. Somebody's chatting in. Thrust side, good JT, good. So we have our major thrust side and our minor thrust side, and it's actually in this next chapter where it talks about that.
This is where the most wear would occur if there is wear in the cylinder. So I'll call this position 1, and I'll go down just below the ring ridge here. So just down about a ½ an inch or 3/4 of an inch into the cylinder. And I'm going to rock this and watch that needle go round and round, and it stops right there. And on this dial, each little tick mark is a 10,000th of an inch, and then the large numbers represent 1,000th. So this is actually just slightly more than 2,000ths of an inch larger than the specification we set the micrometer to.
Can you guys understand what he's saying? So even though it's not lined up with 1 or 2, you can count it from 0 being this way. So 1, 2, even so going to 9 to 8. Yeah.
In fact, to be specific, it's 2
back this up for a second.
thousandths. Represent 1,000. This dial, each little go round and round, and it stops right there.
Can you see why he's saying it stops? It's because the needle reverses positions. So it starts to spin one way, and then at the point where he is perpendicular to so that he's straight up and down in that cylinder, the needle actually reverses positions, and then he goes forward again to get the exact measurement of where it's at, because it's calibrated for that cylinder's bore size. He set his micrometer to the size it should be. Then he set his bore gauge up to the micrometer. Now he stuck the bore gauge in the cylinder, and he's looking for the position where the bore gauge is completely straight, where the needle starts to reverse. And now he's actually going to take the measurement of the cylinder with the bore gauge. It's a much quicker way of a much quicker and accurate way of measuring the cylinder. Like I said, because when you use a telescopic gauge, you can't tell exactly where the telescopic gauge is straight up and down on the cylinder. Okay, so we're at the point where he's making sure that it's straight up and down, and then he's going to start taking the measurement.
And on this dial, each little tick mark is a 10,000th of an inch, and then the large numbers represent 1,000th. So this is actually just slightly more than 2,000ths of an inch larger than the specification we set the micrometer to. In fact,
if it was smaller than the specifications, which side of the 0 would the needle be?
Goes out of spec.
If the taper, we'll say, and very rarely is this the case, but we'll say that especially on the top here of the thrust side of the cylinder, we'll say that this needle was on the right side of 0. We'll say, I don't want to say positive or negative because that might confuse you, but if this needle, when he set it to the perpendicular point, if it was on the right side of the 0, what would that mean? Because let's go backwards. What did 0 account for here? When he set up the tool, what was 0? What did that mean? And what do you think, Christine? Do you remember? Remember he was moving the dial, and the 0 meant that there was a meaning for that 0. Let's see somebody's chatting. Right, JT. So it's where it's straight. So the perpendicular point of where the perfect right angle to the tool meant that the tool was completely straight in its bore. So the 0 point meant that it was straight in its bore. When it goes to the left of the 0, it means that it's larger than what the spec was, right? And if it was to the right of the 0, it would mean that it's smaller. Does that make sense? Okay.
Back to be specific, it's 2.4 thousandths of an inch. So I come here to position 1, I'd write 0.0024.
You guys see why it's so important to understand the placement of your decimal points, also where you're measuring. That's why I went over that exercise, because when we start measuring in, below, the thousandths mark, you can make mistakes there easily. He's at 0.0024, so 2 thousandths and 4 tenths of a thousandth.
Now position 2 I'm going to do here, and then position 3 like this, so that we're just slicing the cylinder into equal slices here. So position 2. There, it's about exactly 1,000th of an inch.
So what's he looking for at this point? Before he took the measurement of the 1,000, because it's, each one of these is 1,000, each line is 1,000, or each whole number is 1,000, and each one below that is 10 of 1,000. So what is he rocking the tool for?
Play.
For play? We just talked about this a minute ago. What is he doing when he's moving that tool back and forth? Yes, see how the needle's bouncing back and forth? What is he looking for?
Find where?
Not yet. Not where. JT is not. He's not looking for where yet.
They never see his stuff yet.
That point where the needle's bouncing left and right and left and right. What does that do? What does that identify?
That it's not straight.
Taper.
Not yet. He didn't take that. He's not looking for that number yet. He's looking where the tool is straight up and down in the cylinder. Because if say when he slid the tool down, yes, but if he slid the tool down and say it was a little bit to the left or to the right, what you're trying to do is find where the tool is straight up and down, so that we know that the measurement we're taking is accurate. When he's rocking it back and forth, he's looking for the point where that rock in the needle stops. The needle will stop bouncing left and right at the point where it is the straightest in the cylinder. Because if we were to the left or to the right, obviously the measurement we're taking is off by however many thousandths we looked at it. So right now he's trying to bounce the needle until he finds the exact point where the needle wants to rest on its own, and that will identify that the tool is straight up and down in the cylinder. Okay, then once he reaches that point, then he's going to take a measurement, which he already said he's at about 1,000th of an inch bigger than the specifications, right?
There, it's about exactly 1,000th of an inch. And position 3 will be like this. And right there, it changes direction, so it looks like it's right on the 1,000th of an inch mark again. So what these represent is how much larger than the specification the cylinder is here.
At the top of the cylinder. So we're going to take a measurement at the top, and we're going to take a measure at the bottom to show that it's tapered, how much bigger it is at the bottom or the top. Because after an engine has been used for a given amount of time, what do you think happens inside the cylinder? When the cylinder is brand new, it's a perfect cylindrical shape, right, at the bottom and at the top. But what happens when the engine runs, we'll say for 10 or 15 years of hard use? What happens to the cylinder? Especially with the thrust of the piston. It gets worn, right? I heard somebody say that. Okay, so when it wears out, what happens to the material in the cylinder?
Starts to
shaving off metal.
We're basically shaving off metal. So at a certain point, it becomes too out of round, and if we cannot machine that out of round out of the cylinder, we either go to a larger bore size, which means that we have to get larger pistons and larger rings to match the bore of from the machinist boring out that block. Okay, this is exactly how I want you guys to make your charts when we start measuring the engine. So you're going to make a cylinder 1, cylinder 2, cylinder 3, and cylinder 4. Everybody has a 4-cylinder engine because I wanted to keep everything simple, so everybody does their own cylinder measurements. That way you guys all get your own experience with the measuring tools and that particular task. Okay, so let's watch the next part. He's going to go to the bottom. Now that he has position 1, 2, and 3 for the top, he's going to do position 1, 2, and 3 for the bottom.
So I'll do the same thing at the bottom of the cylinder. Position 1 at the bottom. Looks like it's about 18 10,000ths or 1.8 thousandths. Try it one more time. Or 19, depending on where I move it to, there's a little bit of variation.
Okay, so you guys saw what he did. He went a little bit further. It rotated down to the lower side of 3, in between, it's like 3.5 thousandths. You guys got to use some common sense here and look at the tool when you're using it. That we're looking for the perpendicular point of the tool being straight up and down, right? If you start to move the tool and it goes to the opposite end and starts rocking, but you look at the tool and it's like cocked, to like 10 o'clock or 2 o'clock, there's obviously something wrong with your where you're trying to calibrate to 0. Okay? So it's going to take some time and using the tool, practicing with it. But once you start using the tool, it'll become apparent, especially when you're trying to calibrate it to 0.
So we'll say 18. Okay, now once we have these numbers, here's where we can calculate our taper and out of round. So if I look at position 1, top and the bottom, I'm going to come over here and say, what was the difference between those two numbers? And it's 0.0006, right? 6 10,000ths of an inch. And I'll do that all the way through here. In this case, there was 0.0001. And here, it's 0.0008. The largest of these three numbers is this one. So I'm going to call that my taper. The most taper that I found here was 8 10,000ths of an inch difference between the top and the bottom of the cylinder. Now to find my out of round, I'm going to compare these to each other. What's the difference between the largest and the smallest number? It looks like it's 0.0014. And here, 0.0007. It's the difference between the largest and smallest measurements we took. The larger of these two numbers, obviously, is this one. So that's my out of round.
Then you would stop at this point and look at your specs that you guys all have on your computer or printed out. So I don't know if you guys want to do it this way, but you could actually make like an Excel spreadsheet with all these measurements if you wanted to, and then just type it in, or you could write it down. It's up to you. But however, you're going to have to submit these measurements to me in a task sheet. So I think if you were to be creative and put it in an Excel spreadsheet, you can actually just copy the file and just not have to type anything into the chart. You could just send me a chart that way. And you're gonna have to do it for each cylinder. So identifying which cylinder you were working on would help. Because you could just, if you copied and pasted, if you were in a group, you could do it that way as long as you put like cylinder 1, like Jason's, or cylinder 2, I don't know who else, Shane, something like that. Okay, hold on, guys. Hold on. I gotta be right back. Hold on.
Meow. The dogs stay barking.
Has anyone got any liquid?
Huh?
Roy, go
Anyone?
buy, cuz.
They're still open, you know.
They
are? Yeah, I just went yesterday.
I
What time
think
do you close? What time
High
do you
Five
open?
is the only one that's open.
Oh shit, you're out of liquid. Oh, that sucks.
Oh, I am out of liquid.
Holy
High Five
shit,
is the only
you're
one open.
22, dude.
Yeah, I just don't know what time they open. That's why.
Go 5-0.
What
Open
time?
at 9 o'clock.
9 o'clock.
Yeah.
Shoot.
Because they're not saying it's a vape shop. They're saying it's a pawn shop. You know how he has that side business?
The fuck?
Huh?
What Dylan?
He runs his like gold shop out of the vape shop. So if you call High Five, they're gonna say hi, aloha, gold buyers. They're not gonna say High Five anymore.
Oh, okay.
Jason, what have you done to your Honda? You put a new intake on it, right?
No, it never fit. So I bought a new. I was gonna put ITBs, but they don't make a kit. You gotta you gotta buy so much shit. They don't sell like a single kit. So I just bought a different intake. The best one. Not the best one, but I just bought a new intake. But I don't know. I put a new Honda inside.
Nice.
I don't know.
What's wrong with the VTEC?
My solenoid's always been giving me problems, but I don't know. I don't know why I'm not getting enough oil pressure. Like
the driver, not the car.
No, you remember we did the compression test and the thing came out garbage.
Came out 170.
Oh no, it came out like bad. Remember, it was coming out the intake and the exhaust.
I know. I fixed my vacuum leak.
I don't know.
Because fuck, what is it called? I went take apart because when I was taking off my intake and stuff like that, I took off everything.
Dude, you're dumping so much money into that car. You should have just sold it.
I only spent $1,000 on that car.
Only.
All right, you should boost your
I'll
86,
buy it from you
dude.
for $6,000 then.
Hey, not to mention the amount of work you put in.
Hey,
The
that's
time.
for
Time
experience.
is money.
Whew.
It's called dedication, Dylan.
So sorry, guys. I'm working on my septic system, and they delivered a bunch of parts for it. Anyway, let's go back to the video.
Now, you'll say, what was your exact bore measurement? So I'll come back to my specification here. 3.7795 was my specification, and I find the largest number that I measured, which was this one, and I add 0.0024 to that. So my bore measurement, the largest measurement in that bore was 3.7819 inches. And now I've taken all of the measurements, and I can compare those against my specifications and find out if I need to do anything with my cylinder, if I need to have it bored out, or if it's okay to use. As long as everything falls within that specification. And I've also got specifications for out of round and for taper. As long as these numbers fall within those specifications, I can reuse the cylinders like they are. I can just hone them and reuse them. Otherwise, they have to be bored out. So one thing to be aware of is as you take this measurement, but if it's to the right of the zero, it's actually smaller than the specification. So in this case, it's to the right of the zero. It's smaller than the specification that we set the micrometer to. That doesn't happen often. Cylinders don't get smaller, but for some reason, either our specification is wrong or the cylinder is distorted, but this is showing us it's 3,000 smaller. If, on the other hand, it stopped over.
You guys remember I was talking to you guys about this earlier. If you go to the left, it's larger, which means your cylinder measurement is larger. If you go to the right of the zero, where you would have calibrated to the exact number your cylinder is supposed to be, it would go smaller. So if we're measuring our taper, that's when we would see it go smaller than maybe our wear measurement. Okay.
Over here on the left of the zero, somewhere on this side, that tells us that it's larger than the specification, and that's most typical.
Yeah, it's very rare you're going to see that it's larger, because how are we going to add material into the cylinder? You know what I'm saying?
Milk lead on top of it.
What?
Aloha, Maui homeowner. Do you have a power meter like this on the side of your head? You qualify to your Maui electric.
Oh, bless you.
Thank you.
Okay. Does that make sense to everybody? And we will go over this again in class before we actually do the measurement. But if you could watch it a few times, pause it, back it up to see what he's doing, would be really important because it'll help you guys understand how the tool works. Before this, I would show it in class, and I'd have everybody stand around me, and I demo it, or I demo it for a group. However, I felt like students really weren't understanding how the tool worked because they were watching, but they weren't necessarily able to watch that action over and over again. So I think that if you could watch that video several times and understand what he's doing, and if you have questions about the video, you can always email me or message me, or we can bring it up in a review. It will help a lot. Okay. What time do we start? It's 10 o'clock. You know what? Before I let you guys go, let's go into some of these slides for today, okay? Okay. Is that okay with you guys?
Yeah.
Okay. Can everybody see this? Does it say CDX? Is it the title page? Okay, good. So it's chapter 20, engine block, components. Now I want to show you real quick. This is all the tasks for this one chapter. So we have disassemble engine block, clean and repair components, for inspection and reassembly, deglaze and clean cylinder walls. We haven't gotten to that point yet. I think there are 2 groups that start disassembly. So some of you still need some time to disassemble the engine. Then we're going to inspect the crankshaft for straightness, journal damage, keyway damage, thrust, flange, and sealing surface condition and visual surface cracks, check oil passage condition, measure end play and journal wear, check crankshaft position sensor, reluctor ring. And then the next task sheet is inspect main and connecting rod bearings for damage and wear. So this chapter is going to cover how to inspect all those components. It's going to identify piston and bearing wear patterns that indicate connecting rod alignment and main bearing bore problems. And then inspect and measure cylinder walls, sleeves for damage, wear, and ridges, and determine needed action. Most of the engines that you will encounter will just have a cylinder wall. Some engines, like on the heavy duty side, like a lot of diesel engines have sleeves inside their cylinders that are able to be swapped out so many times before the engine is done. Or the engine might have to be bored out and a larger sleeve might have to be installed. But most of the engines you guys will encounter or work with will have just regular cylinder walls. Okay, the next task sheet is inspect and measure piston skirts and ring lens, and determine needed action, and then inspect auxiliary shafts or balance shafts, intermediate idler, counterbalance, and or silencer. Shafts, inspect shafts and support bearings for damage and wear. Okay, and then so that's all the task sheets for this chapter. Then it goes into the knowledge objectives, what you guys will learn, and then the skill objectives you guys will learn. So we've already covered the major parts of the engine block several times, but let's go over this again. We have our actual engine block. We have our cylinder bores. So this is a 4-cylinder, an inline 4-cylinder engine. We have our water jackets which surround the cylinder bores and our deck. So our deck is what would line up with the deck of our cylinder head. And you can see our core plugs or our freeze plugs, these brass parts right here. And then we start to go into the internal parts of the engine. So we have our crankshaft, our main bearing cradle or the girdle, I think I talked about it, supporting the crankshaft to the block. What's the difference? What could replace the cradle here? What's the job of the cradle? What does that do?
Not just balancing.
The cradle?
No.
What's the cradle's main job, and what could it be replaced with?
To keep it straight.
It is designed for strengthening, but its main job is to support or hold the crankshaft to the block, right? So if you were to look at it a different way, you see these U-shaped components right here? This actually would be your main caps if you didn't have a cradle in your engine. A lot of 4-cylinder engines use a cradle for strengthening the block, so the block doesn't actually twist. But a lot of engines actually use main caps still. Okay, our main bearing cradle or those main caps would hold your main bearings. One would be here, one would be on the top inside of the block, and those are the bearings that support the crankshaft. Then we have on our crankshaft, we have our conrods. It has our conrod bearings, which are different than the main bearings. We have our conrod cap and the conrod cap bolts. So on the conrod itself, our connecting rod, we have our piston, which has our piston pin pushed through it. Sometimes the piston pins are held in place, and probably we'll cover this in the chapter, but they're held in place with either snap rings or they're press fit, which would require you to use a type of torch mechanism or oven, and it basically expands the piston out. It increases the size of the piston so that the piston pin can get pushed out of the piston. So if you're replacing the pistons, you would have to, but reusing the conrods, you would press out the pin within that oven, which we have at the school. I'll show you. I'll show you when we get back there. Okay. So this is like a Subaru engine or a boxer type motor. It's a horizontally opposed engine. So in this scenario, we have our pistons on the sides, and our cylinder heads are on the sides, like a Volkswagen engine. And then I think we watched a video about engine block manufacturing. So this is a foam core of an engine block, and we would pour molten metal in here, and it would displace the foam out. Okay. So there's different types of techniques used for creating steel, cast iron, or aluminum engine blocks. One is the green sand process, one is the shell process, and one is the lost foam process. Okay, this is a foam model for casting. So I think we had a discussion about this early on when we were talking about fuse plugs. I think Kevin might have mentioned it, that when they produce the engine, they form the holes for casting, for pouring out the sand, or are the water jacket areas for the freeze plugs. So engine blocks have voids in them for the water jackets and the cylinders, and it's the use of gravity for molten metal pouring. So they basically pour out of those holes when they're casting the engine, and then the core plugs are used to seal those holes. They're either called Welch plugs or soft plugs. I have actually seen where they sell, because I used to work in Napa, they sold actual expanding plugs here that were rubber. So in case you were stuck in a scenario where you had a rotten or a bad freeze plug, you could actually just screw a rubber plug in here, and it expands to temporarily seal that. And I believe that's what the Welch plug is. But they also, you guys will encounter installing brass freeze plugs here, because a lot of the freeze plugs that come from the manufacturer are steel. Okay. This next slide is showing an engine block being machined. So this would actually be boring the engine block as if it was like drilling this material out. Here's an aluminum block. This next, do you guys have any questions? No. Okay. So this next part is the showing the location of the oil pump, which is on the front of the engine, which is being driven by the crankshaft. This part is the crankshaft, and drives the oil pump. So some of the components of the engine block assembly include the ribs, or webs, or fillets, which are used to provide rigidity to the casting. So you guys see here this webbing type of material they add into the casting in the crankcase. It's there for support and to strengthen the engine block. I have also seen where some people build, like some of you guys watch like some of the engine builds for Hondas. Some of the very small Honda engines or Toyota engines, they're 4 cylinders, were never designed for the amount of torque that people are building them to create. So they actually put, if you're looking at a if you're looking at a 4-cylinder engine, they actually build, besides the cradle underneath for the main bearings, they actually put 2 plates on the sides of the engine to prevent the engine block from twisting and cracking. So that's in the aftermarket side. If you were putting this engine under a lot of stress and a lot more heat than it was designed, especially with bored cylinders, you would have to add on metal plates to make it, to support the engine block so it doesn't crack. Because how sad would it be if you spent all that money and time, you ran a quarter-mile pass and your engine block cracked? Here's another design of ribs, webs, and fillets to design or to support the engine block itself. And then there's the main bearing cap showing the crankshaft. So this is if you didn't have that cradle. So if the the main bearings, when supported by a cradle, it would have main bearing caps like this. So this is a 2-bolt main bearing cap. So you guys might hear sometimes where we're talking about 2-bolt or 4-bolt main engines, and that's what they're talking about here, is how many bolts support this main cap to the engine block. So here's that word, the girdle. So a girdle also helps position the main bearings in the engine block assembly. It also supplies the engine block rigidity and structure and prevents lateral or vertical movement. We haven't covered this chapter, right? No, this is the first time you guys.
No, we haven't.
Okay, good. I'm just checking. But we have covered a lot of the material that's in this chapter, so that's why I'm working quickly through. So if there's something you need me to stop at, just tell me. Let's see. Let me get you guys involved. What's the oil pan for?
Holding oil.
It holds oil, right? It also seals off the bottom of the crankcase, but its main job is to hold the amount of oil that to properly lubricate the engine. The oil. Hello. Oh, okay. It also helps to radiate heat out of the engine, and it helps to reinforce the engine block too. So it has different jobs just besides holding oil. Here's our cylinders. So our cylinders are the large holes in the block in which the pistons move up and down. You guys know this too. They can be machined directly into the cylinder blocks, or they can have sleeves like this. This is a cast iron block. It's got the water jacket on the outside. It looks like probably like a Honda. You guys see the difference here? So the water jackets in A here, they are still surrounding the cylinder, but they don't make a complete circle around the cylinder. So this actually has a little bit more strength than this block here. These are the types of cylinder sleeves. So we have A, which is a dry sleeve, B, which is a dry flange, so it's got a flange on the top here, and C is a wet sleeve, so it's got O-ring grooves on the bottom.
What they didn't explain was because it's different material. How do they account for expansion rates of the different material?
You know what? Let me write this down. I don't know. Nobody's ever asked me that question, Kevin.
Yeah, because I mean, when you put a steel sleeve in an aluminum block, you're going to get different expansion rates.
Yes, yeah, the steel is going to expand way more than the aluminum, right? So, are you asking like what prevents it from cracking, or?
Well, yeah. How is it that it doesn't crack the block?
Okay, I'll look that up. I don't know the answer to that. It's a good question. I do know, like I was explaining earlier, that most of the engines that have a sleeve in it like this are designed for heavy duty purposes, so maybe they don't have aluminum blocks. But I will look into the engines that do have an aluminum block, and if they are sleeve, how they account for that expansion rate. But I'll be honest, I don't know the answer to that right now, but I'll find it out. Is that okay? Is that fair, Kevin?
Yeah, sure.
Okay. Then we move into pistons. So the pistons fit into the cylinder like a close-fitting movable plug. The piston, besides the energy that the piston absorbs from the expansion of the fuel and air burning, what what is the piston top part of? Dylan, I haven't heard from you for a while. What's the top of the piston part of?
The piston head.
Well, yeah, the top of the piston head. What is that part of?
What is it part of?
Mm-hmm.
It's part of the combustion chamber.
Good, the combustion chamber, right?
Yeah.
Okay, good. So it says right here too in this picture, the piston is the movable floor of the combustion chamber that extracts energy from the burning gases. So if you think about it, the piston, the top of the piston design can actually, what can that do? What can that change? It's in the next couple slides, I believe.
Is it pressure?
Yeah, we can increase our we can
Use
actually
explosion.
increase our compression or decrease our compression depending on the design of the piston head. Yeah, so it's what's the next slide here? I think it's right about, or maybe it's further than that. Area of piston head shape in about 4 or 5 slides. It shows the different types of piston head shapes. Here we go. Here's the next slide after 1 of 3. So here's 2 of 3. This is our wrist pin design, which holds our piston to our conrod. So it's on this side. This goes onto our where does this side of our connecting rod go to?
The cam.
The cam?
The
Crankshaft?
Crankshaft. Yeah, there's 2 moving parts, those 2 rotating parts like that. The crankshaft and the camshaft. The crankshaft is responsible for holding the conrods to the, connects the conrod to the piston. So this one has actual snap rings that holds the wrist pin to the conrod here. And then it's called the floating wrist pin. Then we have, this is we don't have this fixture at our school, but some of the other schools I've been to have this, where you lay the conrod down on this platform and it heats up the conrod so that it expands, so that you can get the pin either in or out. They call it a press fit pin. Do you guys have any questions?
No.
Then we can talk about our major and minor thrusts. So each piston has a major thrust face and a minor thrust face, and that's actually why there's a piston pin offset, which is showing on here. So the piston pin is not exactly in the center of the piston, and that's so that it can have that motion for major thrust and minor thrust. Otherwise, it would actually start to knock around in the cylinder much earlier on than it was designed. Well, from wear, but the transfer from one piston skirt to the other can cause piston slap. So if it was in the center, exactly in the center, you would get piston slap much earlier than from wear, like I said. So our major thrust is on. So if we look at our piston going up and down, our major thrust is when we have combustion and it forces our piston down, and our conrod's going clockwise. It pushes it, and our major thrust side is our left side of the piston on here, and then our minor thrust side is when our piston comes back with our crankshaft and gets pushed to the upper right hand side of the cylinder. So one side of the cylinder should always be worn more than, and one piston face should be always worn, not face, the skirt should be worn more than the other side, and that's called your major thrust angle or face of the piston. Okay. This is the part I think that Archer was asking me last time, the heat dam slot. and the heat dam slot was designed there to prevent the piston from expanding too much, like we had talked about earlier on in the review. So, because obviously pistons expand, like everything, they expand as they heat up. So the methods that can help control piston expansion involve using steel struts or ribs or expansion slots in the skirt of the piston, or slots called heat dams, and that's what this is right here, is the heat dam. Let me get to piston head shape. Okay. So the piston head shape is the shape of the piston determines or depends on the shape of the combustion chamber. So it also depends on how far your valves travel out in the combustion chamber. So for example, if we had a flat piston, our valves can only travel out so far, which would limit its amount of air, or it would limit its travel, really is all it's doing. And then if you had a dome piston, it would also limit its travel. So like some of you have seen in class where some of the piston tops are different and they allow the valves to open up, or they allow the combustion chamber to be smaller so that the valves can open up a little bit further into the piston top. It's also dependent on the manufacturer and the type of engine that it's in. The top of the piston where the valves get pressed into are called the valve relief areas, and it prevents the pistons from hitting the valves or the valves hitting the piston. So most likely those types of engines are interference engines. And then the piston head design affects compression ratio. So we have our flat piston here, our concave piston. This is like a dish type. We have a dome type here. We have actual added material on top to create a dome, and then we have recessed piston. So our valves can actually come down into this type of piston, and this one too. So forging and casting are used to manufacture pistons, and the two versions of the cast piston are cast aluminum with steel struts, or cast aluminum with 16 to 19% of silicon, called the hyperprotective piston. That's what we're talking about in the beginning of class 2. And then hyperprotective pistons are stronger than pure aluminum pistons and are used in many applications. On the right hand side, you guys can see here this moly coating, which is on the side here, which is a piston coating. So black moly is coating reduces friction between the piston skirt area and the cylinder wall. And then the ceramic coating, like the one below here, this gray one, prevents the piston metal from absorbing heat as quickly.
How long would that black moly coating last before it wears off?
No, I don't know. I guess it depends on how you treat the engine. If you don't ever change the oil, or you don't maintain it very well, I guess it would wear off quicker. But we worked on engines that had 100,000 miles, and they still had that coating on it.
Okay.
Yeah. Okay. What time is it? 12:13. Okay. Let me get through a couple more slides, and I'll let you guys go. Okay. So compression ratio. Compression ratio relates to how tightly the air-fuel mixture is compressed in the combustion chamber. So our compression ratio, if you were to break it up, is, if you look at this picture, is 1 of the 10 parts of the cylinder as the piston comes up the top dead center. So an increased compression ratio can increase compression pressures, right? And we can get more power from that expansion because we're squeezing the air and fuel molecules into a smaller space. When they explode, we get more power out of that combustion chamber. Okay, compression ratio can be raised in several ways. Effective compression ratio is the. Oh, let's talk about how the ways that they can be raised. How can we do that, guys? We can raise the compression ratio on purpose or not on purpose. Let's talk about some of the ways we can raise the compression ratio on purpose.
Domed piston crown.
Sure, a domed piston. So we're adding more material into our combustion chamber, which shrinks down the compression chamber size, right? What else can we do? What would be the opposite of what happened in your engine, Jason?
Me?
Yeah, you're Jason. How else can we change the compression ratio or increase the compression ratio?
Increase?
Yeah, Kevin already said to put a domed piston.
Does that count as like, what is the word? Like decreasing the area in the combustion chamber?
Okay, so how would we do that? What's another method we could do that? And that's why I said I brought you up, because it's the opposite of what happened in your engine.
How much gaskets you have, Jason?
Yeah, the stacking or like a thicker head gasket.
Yeah, so if we did the opposite, if we made
That would decrease the compression.
right, it would increase the compression if we took out those head gaskets, right?
Yeah.
Yeah. Another method is by shaving the head, right? If we shave the head, then we're shrinking the space, the combustion chamber size, down a little bit. Okay, so what are ways that what's a way that could be we can increase the compression ratio, and it wouldn't be something on purpose. It's not something that you would do to the engine to increase the compression ratio. Maybe I'm not asking this in the right way. It's a cause and effect kind of problem that can happen to an engine which increases the compression ratio. What could cause that?
Well, you said it, shaving the block or the head.
Okay, I know, but that's something we would have to do to the engine. What could happen as a cause and effect? It's kind of a problem happening to the engine over a period of time that we wouldn't have a part of.
Warping?
No. That's why I said cause and effect. I don't want to give you the answer by giving you part of the question. So I'm trying to choose my words carefully in order for you guys to come up with the answer.
Say the question again, Lawrence.
Okay, so my question is, what is another way that what could cause the compression ratio to increase in an engine that we would have no control over, and it would be most likely due to it would most likely be caused by a non-maintenance kind of situation.
Carbon buildup.
Carbon buildup. Good, Jeff. So we could have an injector that's leaking, or we could have we didn't maintain the oil or something like that, and we get an increase of carbon buildup around the valves or inside of the combustion chamber, and that can cause the compression ratios to increase as well because it wasn't designed to be that way. And we could actually get misfire conditions from those type of scenarios too, because we now have a piece of charcoal. If you think about it, it's a piece of carbon inside of the combustion chamber, and now we've also increased the compression ratio, which is now making the combustion chamber hotter. Does that make sense? And so now we could have a piece of carbon that is exposed to high pressures and high heat, which can turn into a piece of glowing charcoal, and the glowing charcoal can cause pre-ignition before the piston reaches top dead center. That the air-fuel mixture that's being compressed can actually be ignited. That can cause a problem. Okay, good.
Just talking to myself for a good 5 minutes. Forgot I was muted.
an effective compression ratio is the volume above the piston when the intake valve just closes compared to the volume of the piston at top dead center. So we're looking at the ratio between the piston being top dead center and the piston being top dead center when both valves are closed. So the exhaust valve will be closed and the intake valve will just have closed, and we will take that measurement. And that's how we get our compression ratio.
Is there any easy way to figure out how to calculate the compression ratio when you have shaped piston heads and stuff like that?
You would have to CC the piston head. You would have to CC every part of the, you would basically be taking a volume measurement of every component in the cylinder and the piston and in the combustion chamber. But you know the easiest way to do this. You're asking me the easiest way, and that is already calculated by the manufacturer. So when you buy the parts, they will tell you this will raise your compression to 13 to 1 or 10 to 1, something like that. That's the easiest way to do it because they've already calculated for the stock compression ratio, which you can find in your specs, and then they would add in either a dome piston volume, what it's subtracting out of the, or adding to the.
Well, that's what I meant. Without trying to go into calculus to calculate the area under the curve of that dome, is there just an easy way to do it?
Yeah, it would be just talking to the manufacturer because they've already calculated it for you. That's the easiest way. There's no other way of doing that I know of. Mostly it would be ceasing the engine, the volume of everything changing. Let me just cover the piston ring section here, then I'll let you guys go for the day. So right here you guys can see there's 3 different piston rings. So our compression ring seal and create a closed fit between the piston and the cylinder wall. Which one is our which is our compression rings, guys?
The top 2.
The top 2, yeah. And then we have our oil control rings, which hold a small amount of lubrication oil, and that's this right here. When you guys get to this part where you take the rings out, you'll notice that this oil control rings actually is combined of 3 different parts. There's like a top ring here. There's like this spring, wavy spring thing that's wrapped around the piston, and there's another support ring here at the bottom. Okay. The piston rings can be square, tapered, flat, or slanted on the ring surface. And it says here too, the compression rings are the 2 top rings. Okay, the piston rings ride in ring grooves in the piston. Most common arrangement has 2 thin compression ring grooves and 1 oil ring groove. So when we take this apart, we have special tools for cleaning these ring grooves out because carbon tends to build up on inside of the ring groove, and besides using, you can't really you don't really want to stick a screwdriver in here and mess this up or break this. So we have a special tool that actually clamps the piston inside of it, and it rotates you rotate the piston inside here on the groove to scrape out any built up carbon if you were reusing that piston. And then the ring lands support the piston. So it's kind of like when we looked at what component can you guys think of that we looked at that was similar to this, that was inside of the automatic transmission? It also used lands and grooves as well, and valves. You guys remember the spool valve?
Yes.
Yeah, the spool valve used some similar terms to the lands and JT. Oh yeah, good job, JT. Sorry, you're a little. It's always a little delayed getting into the chat, but yeah, you're right. It was the spool valve. Okay. So, oh, there we go. There's the tool for cleaning the piston rings out. Oh, that's an installer. Okay. The tool we have actually kind of looks like this. This has little teeth, adjustable teeth for different size ring grooves. Anyway, why don't we stop here? I kind of went way longer than we usually do, and when we come back on Thursday, I'll start with compression. Okay. You guys there?
Yeah.
Okay, does that sound fair? Or you guys want to keep going? You guys all I know. Well, learning like this is good. It's a little bit harder than in the classroom, especially because I can't show you the parts. And we haven't been taking breaks. So if that's okay with you guys, we can stop here and come back on Thursday and cover compression rings.
Sounds good.
Okay.
Hallelujah.
I will try to sort out Electude. So by tonight, it should be working. So please keep trying to check in with Electude and logging in. But if you please try to follow up with Electude so you guys can look at some of those interactive activities too. Okay. Okay,
Yep.
guys. Thank you for coming today. I'll see you guys on Thursday.
Yep. Thanks, Lawrence.
Okay,
Cheers,
thank you.
Lawrence.
See you, Lawrence.